Hi guys, I'm here at the discrete math cover sheet, and what I'm going to do is I'm going to click on 1A, graph theory and Euler circuits notes. And then I'm going to open that up here. All right, graph theory and Euler circuits. So Leonhard Euler is this guy here, and he's a Swiss mathematician who kind of laid the foundation for the geometry of location, which would later evolve into graph theory. So what is graph theory? Well, it's the study of graphs, which are mathematical structures that are used to model relationships between objects. And in this case, those objects are typically locations. So really, graph theory is nothing more than just the study of relationships. Now, one of the big things we look at in graph theory are called routing problems. And that's where we look at how we deliver goods and services to different destinations. So we've got a few rules of the road here, folks. Number one, if there's a direction of traffic, you have to follow it. Number two, if there is no direct route from A to B, you can't make one. No off-roading, no creating your own edges. You just can't go there. All right. So let's see if you can trace each of these or any of these without lifting your pencil and without retracing any lines. You've probably seen this. I know I've seen these ads on Instagram and on games and such on my phone where they'll say something like, only 3 people can trace this without lifting their hand or repeating a line. And once you kind of get the ins and outs of graph theory, you'll be able to look at them and say, oh, you're right. Or you might be able to say, nope, wrong. Sorry, sir, you can't. So let's see. I'm going to try one of these. Grab my drawing tool here, and I'm going to look at this first one, and I'm going to start here. And you can see, oh, that's white. White is not good. Let's get red. As I draw here, I'm going to go ahead and do this whole thing, and I didn't retrace any lines, and I didn't lift my pencil. So try the other 3. See if you can do them. If you can, awesome. If you can't, think about why not. Why is it possible with some shapes and not others? And we'll learn more about that later in this unit. But for now, as I'm drawing everywhere, I am done drawing, thank you. Let's talk about what a graph is. So again, we said that a graph is a mathematical model of a relationship, but really it's a picture. For us, it's a picture that's made up of dots that we call vertices and lines that we call edges. So the order of a graph is the number of vertices that it has. And we list the set of vertices using the convention V of G equals. And then you make those brackets for your set and you list your vertices separated by commas. Now, remember, just like in geometry, we name a vertex with 1 letter. For sides, that gives you the size of a graph. It's the number of edges that it has. Now we can list the set of edges using the convention E of G equals, little brackets, and then you list your edges. Remember, just like in geometry, an edge is listed using 2 letters, the vertex at each end. All right, so let's look here. Well, I've got 1, 2, 3, 4, 5 vertices, A, B, C, D, and E. So my order is 5. And my vertex set, V of G, is A, B, C, D, E, separated by commas. I've got 8 edges. Let's check. 1, 2, 3, 4, 5, 6, 7, and the loop makes 8. All right, so my size is 8. Now, let's list our edges. So E of G equals, from A, I have AB and AD. Moving to B, I'm not going to say AB again because I've already listed it. AB and BA are the same edge, but I will list BC and BE. Moving to C, I'll put CE, CD, but then I have to put CD again because there are 2 lines from C to D. and that's why it's listed twice. Finally, I go to my loop here, E to E. That's my final edge. And you'll see here that in this practice, it's done the same way. You have 8 vertices, so your order is 8, 11 edges, so your order is 11. Here you don't have any double edges, but you do have that loop at the end, the GG. All right. So here, now this one's interesting because this is a graph. It's showing that you have these 4 objects, but it's also showing that there's no relationship between them. So they exist, but they're not connected. That means that our order is 4, V of G, list them out with the commas, but then there are 0 edges, so size is 0. Note that you still need to write E of G, but then you use the empty set symbol here, or you can use the 0/, the null symbol, or you could just write empty set. The big thing is don't write 0. All right, let's look at this one. 7 vertices, A, B, C, D, E, F, G. Yep, 7. So our order is 7. And then 1, 2, 3, 4, 5, 6, 7 edges. All right. Now, do you see how not every side or vertex is connected to the rest of the graph? So let's talk about what that means. So a graph can either be connected or disconnected. In a connected graph, all vertices are connected in some way, meaning that I can start at any one vertex and make a path that goes through every other vertex. I can do that here in this connected graph. However, here, there's no way for me to get over to E or D because there's no edge connecting it to the rest of the graph. So this is a connected graph, but this is a disconnected graph. Bridges are what take a graph that could otherwise be disconnected and make it connected. So let's see. A, B, C, D, E, my order's 5. 1, 2, 3, 4, 5. Loop for 6, loop for 7. So my size is 7. And because I have 2 loops, remember I have to put EE twice, and it's connected. But let's look, do I have bridges? This time I am going to grab that white. If I remove AD, do you see how the graph becomes disconnected? Or if I remove DE, the graph becomes disconnected. But what if I just remove something like AC? That graph is still connected. What if I remove one of the loops? Doesn't matter, graph is still connected. So that bridge is one that if we remove it, the graph becomes disconnected. So we have 2 at AD and at DE. All right, now here you were given the instruction to draw a graph, and you were given 4 vertices, ADLR, and you were given 6 edges. You were told to connect AR twice. You see we did that. Then draw AD, AL, DR, and DL. Now see, this is a connected graph, right? Nothing's floating off by itself. And I don't see any bridges. There's no side here, no one side that if I removed it, the graph would become disconnected. All right, let's try this one. We've got a baseball schedule that we're going to draw a graph from. So what you want to do is you want to make each city a vertex. And then for every game between the cities, you connect them. So like Pittsburgh and Montreal. Pittsburgh and Montreal play each other twice, so there's going to be 2 connections between those vertices. I believe New York and Philadelphia play each other once, so there will be 1 connection. Go through and connect them, and you'll end up with something that looks like this. So our order, well, there's 6 cities, so our order is 6, and there's 8 games, so our size is 8. And if you look, this graph is connected. All right, so we're going to stop here and go back to our cover sheet, and we're going to go to our first practice set. Now there's one thing in this practice set that I need to go over with you, and that is, what does it mean to find the degree of a vertex? Well, That means I look and say, how many edges connect to one point? So if I look at A, 1, 2, 3, A has a degree of 3. What about A here? Well, nothing. So A has a degree of 0. Let's look at X. Now it's every connection. So the loop does count twice. 1, 2, 3, 4, 5, 6. X has a degree of 6. So go ahead and list the vertices and edges for each of these. So your V of G and your E of G, and then list the degree of each vertex. Go through and answer the rest of the problems, and then I will see you later for the next part of this